Namaste dosto. Imagine you're watching a car speeding down a highway. How do you figure out its speed at just one exact moment? Not over a whole minute, but in that blink of an eye. Well, that's where derivatives come into play. Today, we are going to explore the idea of instantaneous change, how derivatives capture the speed or rate at a particular instant. Let's start simple. Suppose you have a function, call it f of x, representing some changing quantity. If you want to know how fast it changes between 2 points, say x and x plus h, you look at the average rate of change. This is given by the difference in function values divided by the difference in x values, which we write as open parenthesis f of x plus h minus f of x close parenthesis over h. Let's put on our geometry hats for a moment. Top hat, imagine a smooth curve drawn on the xy plane. Pick a point x on that curve. Draw another nearby point at x plus h. Connect them. What you get is a secant line. The slope of that secant is just open bracket f of x plus h minus f of x close bracket divided by h. Now, as we move that second point closer and closer to x, that secant slowly becomes a tangent line, kissing the curve at just one point. And that's when the limit as h approaches 0 gives us the derivative f dash of x, the exact slope of the tangent. So, geometrically, differentiation is like zooming in infinitely until your curve looks like a straight line. Pretty cool, right? You're basically seeing the microscopic slope of a curve. Now let's jump into physics for a bit, because math and physics are best friends. Suppose you're driving a car, and your position at time t is given by s of t. If you check your odometer between 2 times t and t plus h, your average velocity is open bracket s of t plus h minus s of t close bracket divided by h. But what if you want your speed at this very instant, right now? Then, as h approaches 0, that becomes the instantaneous velocity, v of t equals limit as h tends to 0 of open bracket s of t plus h minus s of t close bracket divided by h. Or simply, v of t equals s dash of t. So, derivative of displacement gives velocity, and derivative of velocity gives acceleration. That's why derivatives aren't just math symbols. They literally describe how fast your world is changing. Every time you press the accelerator pedal, you're practically taking a derivative with your foot. Alright, back to pure math for a moment. Chart with upward trend derivatives can also tell us whether a function is increasing or decreasing. If f dash of x is greater than 0, it means the slope of the tangent is positive. The graph rises as x increases. If f dash of x is less than 0, the slope is negative. The graph falls. And when f dash of x equals 0, we might have a peak, a valley, or even an inflection point where the curve changes its shape. Think of it like hiking on a mountain. When you're going uphill, derivative is positive. Downhill, derivative is negative. And when you reach the top or bottom, the derivative hits 0. That's the beauty of derivatives. They map the mood of your function. Let's wrap this up like a good story. Clapperboard, here's what we learned today. Formula 1. F dash of x equals limit as h tends to 0 of open bracket f of x plus h minus f of x close bracket divided by h. That's the limit definition of a derivative. Formula 2. v of t equals s dash of t equals limit as h tends to 0 of open bracket s of t plus h minus s of t close bracket divided by h. That's how velocity comes from displacement. Formula 3. The slope of the tangent to the curve equals the value of f dash of x at that point. And conceptually, derivatives are our mathematical microscopes. They zoom into curves, reveal their slopes, and tell us how fast things change in nature, in motion, and even in finance or biology. So next time you see a speeding car, a falling ball, or a rising graph, remember, derivatives are silently at work describing every instant of change. In the next video, we'll dive deeper into differentiation techniques, and trust me, it's going to be a smooth ride down the calculus highway.